In this video, I'll show you how to solve the ALEKS problem called finding the equilibrium temperature when substances at different temperatures mix. So obviously in this problem, you've got two different objects. They're starting at different temperatures and then they're being combined together and they're going to change temperature until they both have the same temp. For my problem, I have cream that is starting at 10.9 degrees Celsius and I have coffee starting at 83.1 degrees Celsius. They're being mixed together and so the temperature of the cream is going to go up a little bit and the temperature of the coffee is going to go down a little bit, and they're going to both come to a common final temperature. So to solve this problem, we're going to be using the equation QSMAT, Q equals SM delta T. We're actually going to need to do that QSMAT calculation 2 times, once for the cream and once for the coffee, once for each object. This Q is referring to the heat that is being exchanged between the two objects. That's typically going to be in units of joules. The S is going to be the specific heat of our object, or ALEKS likes to call it specific heat capacity. M is the mass of the object. That is going to be in units of grams. Looking through different variations of this problem, it looks like ALEKS is pretty good about not requiring you to do unit conversions. Delta T is going to be the temperature change, the difference in temperature. So I'm just going to write the change in the temp. And that is going to be, it can be in either degrees Celsius or Kelvin, doesn't make a difference. And for this problem, because it looks like my temperatures are in degrees C, I'm just going to put that, that's what it is. So the concept with this problem, like I said before, is that the temperature of the cream is going to be cooling down, and the temperature of the coffee, nope, I said that backwards. The cream is going to be heating up, and the coffee is going to be cooling down. And I know this because the cream is starting out pretty cold. The coffee is starting out hot. They're going to come together to a final common temperature. That means that the cream's temperature is going to go up and the coffee's temperature is going to go down. All of the heat that is being used to raise the temperature of the cream is going to come from the coffee. So as the coffee is cooling down, it's cooling down because it's transferring heat from itself over to the cream to warm that cream up. So I know that the cream is absorbing heat. That means it has a positive value of Q. I know that the coffee is losing heat. That means it has a negative value of Q. And I also know that all of the heat that the coffee is losing is the heat that is being absorbed by the cream. So the numerical value of Q is exactly the same for the cream and the coffee. The difference is positive versus negative. So I can write an equation that looks like this. The value, positive Q for the cream, is equal to negative Q for the coffee. And again, this is because the value of Q, the numerical value of Q, is exactly the same for both of these two objects. Now this is true no matter what your objects are in this problem. There's a lot of different objects in this problem. No matter what the two objects are, you can start by setting this equation up. So what we're going to do next is instead of using Q, we're going to take this equation right here, and we're going to use SM delta T in place of Q. So that means my specific heat for the cream, this is going to get kind of lengthy, times the mass of the cream, times the temperature change for the cream. This would take up less space if my object started with different letters and I could just use a single letter abbreviation. That is going to be equal to negative, don't forget the negative sign, the specific heat of the coffee times the mass of the coffee times the temperature change for the coffee. Now, the problem is asking us to calculate the final temperature of the two objects, and that final temperature is embedded in this delta T. Delta T is not the final temperature. The final temperature, as I said, is in this delta T calculation, or this delta T variable, I should say. So we're trying to kind of isolate and solve for T. But we've got quite a bit more work to do before we can do that. So for your objects, the next thing that I want you to do is think about the value of the specific heat capacity for your objects. Depending on what your objects are, you may need to go to ALEKS's data tab right here and look up the specific heat capacity for your objects. You can find that. For this particular problem, I'm kind of lucky because it says that I can assume physical properties of the cream and coffee are the same as those of water. And what ALEKS is referring to when it says that, it's referring specifically to the specific heat. So it wants me to use the specific heat capacity not of cream, but of water. and it wants me to use that for both the cream and the coffee. It wants me to use specific heat for water. And then, like I said, I'm pretty lucky with this problem because I don't need to go to the data tab and look up the specific heat of water, because they are just gonna, those terms are just gonna cancel each other out in my problem. Now, this is not gonna be the case for every single variation of the ALEKS problem. So for example, I'm looking at one that has brass being dropped into water. And in that case, you would be using the specific heat of not bass. You would be using the specific heat of brass versus water, and you would need to look those values up. And you would need to enter those actual values in. But if you are being told that both of the objects have the same specific heat, or they have the specific heat of water, then that's going to make this problem a lot easier, because we're just going to be able to cancel those out just like that. Okay, now the problem does give us the mass of the object. So there's my mass of cream and there's my mass of coffee. And those I'm going to plug into this equation when I'm ready. I'm not ready to do that yet. The next thing that I need to do is worry about the temperatures, because like I said, we're trying to calculate the final temperature. We're not trying to calculate delta T, and final temperature is embedded in this delta T term. So let's see where we're going to fit this. For the cream, the change in temperature is going to be the final temperature minus the initial temperature. I'm just going to write, instead of writing initial temperature, I'm going to write the temperature of the cream. And for the coffee, the change in temperature is the final minus the initial temperature, which I'm going to write temperature of coffee. T final, that is the variable or the value that we're trying to calculate. The final temperature is the temperature that they both come to together. So the value of TF for the cream is equal to the value of TF for the coffee. That is going to be exactly the same. So what I'm going to do next is, here for delta T cream, I'm going to plug this in that place. So I have the mass of the cream times the temperature change, delta T, for the cream, which I'm going to write as T final minus T cream. And the T cream term, that is my starting temperature for the cream. And that is equal to, do not lose this negative sign. It's so easy to lose this negative sign. Negative mass of the coffee times, instead of writing delta T of the coffee, I'm going to write T final minus T coffee. Now, this problem is going to get a little bit algebra heavy, but that's okay because algebra is super fun. What I'm going to do is expand the multiplication on both the left side and the right side, because this variable that we're trying to solve for is this guy right here. That's the variable that we're trying to figure out, and it's on both the left and the right. So I have the mass of the cream times that final temperature variable that we're trying to figure out minus the mass of the cream times the starting temperature of the cream. And that is equal to, don't forget that initial negative sign, negative mass of the coffee times that final temperature plus, because I've got a negative times a negative, the mass of the coffee times the temperature of the coffee. Now, again, I'm going to highlight this. This TF variable is the variable that we're trying to solve for. So that variable we actually want to isolate, and we're going to do a little bit more algebra. We're going to move this whole entire term over to the left-hand side of the equation so that the two variables, or the two terms with TF, are together. And I'm also going to move this to the right side of the equation to get it away from that TF. So I've got mass of the cream times TF plus the mass of the coffee times TF. I did that by moving that term over. That is equal to the mass of the coffee, T coffee, plus I'm moving this term over to the right-hand side, mass of the cream, temperature of the cream. And now, this is getting tricky. Now we can do a little bit of simplification. So I'm just going to try to squeeze this stuff together a bit and make a little bit more room for myself. So now we can do some simplification. Here again are those TF variables. So what I'm going to do is take that TF variable and I'm going to pull it out, doing more algebra. TF times the mass of the cream plus the mass of the coffee is equal to the mass of the coffee, temperature of the coffee, plus the mass of the cream, temperature of the cream. And I can take one more step. I can divide both sides of this equation by this variable right here. So I can divide both sides by the mass of the cream plus the mass of the coffee. That's going to get rid of that right there. And that's just going to leave us, when we plug all of this in, we're going to be calculating for that final temperature. So let's go ahead and give it a shot. And like I said, I told you this problem is a little bit math heavy, but this is all algebra stuff that we can do. So I'm going to take this and I'm going to just try to fit it up in this space right here. The mass of the coffee, 150 grams. 150 grams. The temperature of the coffee, that's my starting temperature, 83.1 degrees C, plus the mass of the cream times the temperature of the cream. So the mass of the cream is 11 grams and the temperature is 10.9. 11 grams and move this down a little bit, 11 grams and 10.9 degrees C. And then I am double checking to make sure that I've got my data all in the right spot. Coffee, 11, 10.9. And then I am dividing by the two masses added together. So my two masses together, the mass of the coffee plus the mass of the cream. This should give us the final temperature. 150 times 83.1 plus 11 times 10.9. And then we're going to divide that by 150 plus 11. And that gives me a final temperature of 78, to three significant figures, 78.2 degrees Celsius. ALEKS does want this in degrees C, so that works out pretty well. So does this answer make sense? Because I had to do so much math to get to this point. With problems like this, I like to ask myself, does this answer actually make sense? Did I, maybe if you forgot this negative sign somewhere along the way, you might get a funky answer out here. Does this answer make sense? It does. We know that the coffee started at 83 degrees and the coffee was going to cool down to a lower temperature. So 78 is pretty reasonable temperature change. And so that is 78.2 is my answer.